you can flip
It
the
works,
slides.
right?
Yeah, I can see it.
Okay.
It looks great. So let me introduce you first. So the next speaker is Riccardo Rattazzi, and it's going to tell us about EFT bounds beyond weak couplings. So please go ahead. Thank you.
Thank you. I'd like to thank, first of all, the organizers of this meeting for inviting me to give this talk, which has forced me to leave what I've been doing for the last year and go back to this stuff. Okay. Well, I don't know whether I should thank them, but actually, no, it was useful. So, so this is work that was done about a year ago with these people. Okay. I guess a lot has been said about this subject on Monday. Okay. There you have seen where that prime principle constraints from unitarity, causality, and crossing paired with weak coupling are very powerful, and that has to do with the fact that the weak coupling can consistently consider the three-level approximation of the theory, and in that limit you obtain infinitely many sharp bounds. The subject of my talk is to try to present what can be said instead in the case where you cannot make these assumptions, okay? And by the way, I don't just want to say that, oh, if it is not three-level, is not interesting, we should always be strong coupling. I mean, nature has a good feeling, I mean, has a taste for weakly coupled theory, and there's even some indication that gravity unifies with the other interactions in a regime of weak coupling, as we know very well, okay? On the other hand, there are other regimes in particle physics where strong coupling may be relevant. One of these is, well, others where we know it's relevant, say QCD, but another where it may be relevant has to do with electroweak physics and is related to the open question of what is the real dynamics behind the Higgs boson. Of course, it could be just the elementary particle period up to the Planck scale, but there are structural issues that suggest that it could be instead a composite particle, and so that above some scale, which is presumably, which for this to be interesting should not be too high, the Higgs dynamics merges into some new dynamics, which once upon a time was called technicolor. Now we have more refined way to think about that. And now in this picture, the Higgs is a composite particle, so necessarily you need strong interactions. And just to show you how the use of the technology of dispersion relations applies to this case. This was already studied, in fact, about 10 years ago, around the time, around or before the discovery of the Higgs. And I'd like to show you some statements that can concretely be made using this correlation between IR and UV physics that is offered by dispersion relations. And this concerns the coupling of the Higgs to two vector bosons, okay? They say the coupling of Higgs to WW, which you can parameterize this way. In the standard model, this parameter A is 1, okay? And the present fit from the LHC is, I would say, impressive, okay? It's impressive that they are down to this precision. It's 1 within the experimental accuracy, okay? And now, what is interesting is that under the assumption, I mean, if you work at the leading order in the weak interaction, but to all orders in whatever new physics may exist above some scale behind the Higgs, okay? And in this assumption, you write an effective Lagrangian. In this assumption, you can associate, you can relate this coefficient A to the scattering amplitude, to two scattering amplitude of the Goldstone partners of the Higgs. Particularly, you can relate it to the scattering amplitude for the plus and minus charge Goldstones, plus minus into plus minus, and plus plus into plus plus, okay? So then you can write a dispersion relation for the difference of these two amplitudes, and the dispersion relation takes this form, okay? Of course, you don't get a sharp bounce, but perhaps you even get something more interesting. You get a correlation between something you measure, some infrared quantity, and some properties of the UV theory, even the far UV theory. And it works this way, okay? Well, this is coming from a one-time subtracted dispersion relation, so you get a contribution from the arc of integration at infinity which is essentially, this is just given by the amplitude divided by S. This is the difference of these two amplitudes, okay? And then you had this integral, which is the difference of the cross-section for total cross-section plus minus and plus plus. Now, this is, okay, you cannot argue in a completely clean way, I would say, about this, but in all the cases where we have been able to say something about this contribution, it's either positive or zero. It is positive in the case where the Higgs is a weakly coupled object and you have some new gauge bosons up there, like for instance, you gauge the right-handed gauge group, SU2, right? Or as for instance discussed in this paper, if the Higgs is composite, you consider the Reggi's limit, okay? And you consider and you assume that, as it's normally thought to be true, that the leading the leading Reggia trajectory is made of an isospin singlet, then this contribution will vanish. Okay, essentially this is the Pomeranchuk theorem. So in that case, therefore, you see you have something positive or zero here, and then you have the difference between these two cross sections. Okay? So in particular, if you were to discover that A is bigger than 1, then you would have the indication that there is a significant weight of the cross-section in the plus-plus channel. So for instance, if the theory is weakly coupled, and this is dominated by 3 level, an A bigger than 1 implies that you must have necessarily some scalar of charge 2. Okay, and this is already something that was known, but it's nicely seen in a more general way using this symbol. Okay. But it's just to tell you that you can say things that have relevance without necessarily the hypothesis of weak coupling. Okay. Now, of course, you have to correlate things. Now, what I will focus on during my talk is the simplest possible case in the simplest possible situation. That is to say, a single Goldstone boson, namely derivatively coupled scalar in 4 dimensions. I will assume the usual convergence at infinity of the amplitude. And given that we are dealing with the Goldstone boson is derivatively coupled, we also are in a situation where the forward amplitude is well defined. So it's well behaved in the limit where the mass is set to 0. So I'll be working throughout this talk, focusing on the forward limit. Okay, of course, this gives you only some limited set of constraints, but I think what I'm saying, and as essentially already been shown by Francesco Riva on Monday, can be extended in some way also to the non-forward case. So in the paper we wrote 1 year ago, the way we phrase these constraints on the infrared effective theory is through, standard dispersive integral, but we write it in the following way. We find it convenient to package the information in the following way. We perform our integral on this contour, which consists of a contour around an energy S hat that lives within the EFT. And then there is the contour at infinity that you throw away because of your hypothesis. And then what your dispersive integral does, it relates the integral of the amplitude suitably weighted by some power of S on this arc, we call this the arc, to the integral of the imaginary part of the amplitude between this energy and infinity. Okay, so this is the essence of the story. You relate something that you can measure in principle to an integral which contains information both about the IR and the UV. So you have something that you measure in the IR, and the integral gets contribution from both IR and UV in principle. Now notice that the property of the amplitudes are such that this quantity A is always real. Okay, so you can conveniently phrase this relation by using, rather than S, which is integrated between S hat, if you want, S hat is the energy where we do the measurement, and infinity, in terms of a quantity X, which varies from 1 when S is equal S hat to 0 when S is equal infinity. So 0 is the UV and 1 is the IR. Okay, and then you can phrase this integral as an integral of this form, where rho is nothing but the imaginary part of the amplitude, and it's a positive density. So this is simply what you would call the moment of a density distribution. Okay. So once the problem is phrased in this way, the issue of the constraints from positivity and analyticity and unitarity on the coefficients, on the parameters of the effective theory can be phrased, can be seen to be equivalent to the so-called Hausdorff moment problem. Okay. In other words, these quantities, which we call the arcs, suitably weighted by the power or energy to make them dimensionless, are just the moments of this density. Okay. And now the Hausdorff moment problem goes by the following statement. If you consider now a series of numbers Bn that goes from 0 to infinity, okay, starting with the 0th moment to the infinite moment, and you consider what we call the discrete derivative, which is given a series, given a succession of, not a series, given a succession of quantities Bn, you can consider the discrete derivative, okay, which is a new succession where each entry is just the difference of the neighboring one in the previous step. Okay, so now the statement of the Hausdorff problem is this: the positivity of the measure is in one-to-one correspondence. In other words, say that the measure is positive is the same thing as saying that this derivative, that any derivative, okay, if I apply multiple times this symbol delta for k, for any k equal to 0 to infinity integer, all the terms of this succession are positive. So, and if all the terms of this succession are positive, then there exists a density of which these b's are the moment. Okay, so this is just, so all the hypotheses that go into UV physics are contained here. Now, this is the way, say, the Hausdorff problem is normally phrased by mathematicians, but in physics we normally don't have access to all the b's. Okay, and if you look at these constraints here, we're normally interested only in some order in the expansion, and what you will see, and you already know, these arcs are basically correlated with the Wilson coefficients. So the higher the arc, the more Wilson coefficients come into the place, into the game. So pragmatically, it's just a fact of life that we cannot work with infinitely many of them. Okay, we always work with a number of them. And the question is, what is the optimal bound on the finite number of these arcs that follows from this constraint? And this can be phrased in terms of Hankel matrices. Okay, these are all things that are well known, and they can be phrased in different ways. From the different people who work in this area, but that's basically the way you define these Hankel matrices. And then the constraints. Okay, if you want to constrain arcs from 0 to n, you have two classes of constraint. Your constraint that we call homogeneous, which has nothing to do but the positivity of these Hankel matrices, and the other ones that are we call inhomogeneous because they depend explicitly on the energy. Okay, while these other ones here, the only dependence on the energy is through the dependence of the arcs, if it exists, on the energy. Okay, and now let me just put forward that in the case, for instance, of a tree level, the arcs are just constants. Okay, and if you look at the inhomogeneous bounds, these are unavoidably violated for S large enough. So in the tree-level approximation, the inhomogeneous bounds are those that tell you essentially where the cutoff of your description is, where the masses of the states you integrated out are. Now, a few more facts. Okay, even the okay. So I can compute these arcs at any S. Okay, within the EFT, and now if these two arcs, S and S prime, are all within the domain of validity of the EFT, I can relate the arcs at S and the arcs at S prime in terms of things that I measure in the IR. Okay, and as long as, I've defined in the EFT in the IR, by construction, the imaginary part of the amplitude R is positive by construction. So the relation, let's say that if you, so the arcs of this higher scale and this lower scale are related by integrating over a positive measure. And when you go from the UV to the IR, you add some positive measure. And the result of that is that if the arcs that you had at the scale S prime satisfy the Hausdorff constraints, the one at scale S will satisfy it a fortiori. That's essentially the fact that if the effective theory is well defined here, it's unavoidably well defined at lower scales. On the other hand, if your constraints are satisfied at the scale S, then you have to integrate out the measure. So you have to subtract, and you're no longer guaranteed that at the scale S prime, the bounds will be satisfied. Okay. Could be that S prime is outside the domain of validity of effective theory. So it's just to tell you that the strength of the bounds increases with the scale S hat. Okay. So, and the higher the scale you within the EFT at which you compute your arcs, the closer you get to get information about the UV. Sorry, how much time do I have?
You have about, I think you have 10 minutes and then 5 minutes questions after that. So 15 minutes.
Okay, so let me speed up then. So this is made more quantitative by considering our specific case where I have an amplitude of this form, okay? And now, in the theory of this Goldstone boson, the imaginary part at very low energy goes like S to the fourth. That's the leading contribution, the far IR. So now that you know how this goes, then you know how this density goes, and you can look at the integrand of the arc, okay, and whether it's IR or UV dominated. And you very quickly conclude, as it is known, that the lowest arc, n equals 0, the integrand, okay, is dominated at small x. Okay, so if you take x equal 1 here, okay, this is clearly dominated in the UV. That's the one that constrains the leading term in the amplitude C2. The next one, okay, the integrand is 1 over x, so it is marginal. Okay, the integrand is distributed over UV and IR. And starting with the second arc and on, the integral in the far IR is totally dominated in the IR. Okay, if you take the integral is dominated in the far IR. Okay, so essentially you have UV domination here, you have marginal n equal 1, and you have n equal 2 here. Of course, now if I were to start considering truncating and going to a bigger S hat, okay, S hat prime, which is S hat over S hat prime square. In other words, I now redefine my probability and I integrate only up to here. Then I get closer to a situation where maybe these guys start going up and I start getting more information about the UV, okay? And how to see this concretely? Well, to see that, we have to start making assumptions, okay? In order to see how far, in other words, to get information about the UV, we have to go as far in the UV as we can. And let's see how this works. Now let's make the simplest assumption you can make is weak coupling. Weak coupling corresponds to a situation where this spectral density is essentially as a step form, essentially, up to effects of order the coupling, okay? They go to 0 with the coupling. In other words, below the threshold of the heavy physics, which corresponds to some certain x. Remember, small x equals 0 is the UV, and this is the domain where the EFT is defined. So when you're weak coupling, you have this form, okay? And you see the fact that the probability, this density is weighted towards the UV tells you that even if you compute, for instance, some power of rho, like rho times x cubed, okay, this may have a behavior like this, okay? In other words, it's true that in the far IR, the integral is weighted, but if you truncate it sufficiently towards the UV at an energy which is not 0, but sufficiently high, then your arc will constrain genuine UV physics, not IR physics. And the way to see that, well, you see, weak coupling simply corresponds to the following structure of the coefficients of the Wilson coefficients. In this situation, the arcs, as by direct computation, they track the Wilson coefficients. Okay, there is a contribution for Wilson coefficient, but there's always a contribution from the lowest Wilson coefficient, and this contribution grows when S goes to 0. This is precisely when the arc is a high arc, it is dominated by IR physics. So in order to be in a situation where while this thing here is truly the Wilson coefficient, so this is the one that carries the UV information. So you would like, given that the constraints from positivity are imposed on the arcs, you would like this constraint to be directly connecting what you're measuring with UV physics. You want to be in a situation where this can be neglected over this, okay? And using the ordinary, the parametric scaling of a weakly coupled theory, this clearly arises if the coupling is weak enough, if S is large enough. And where is the S where this arises? Where, given the arc N, this arises if S is slightly below the cutoff, but by an amount which is given by a positive power of alpha. Now, that means that there is a small window close to the cutoff where you can essentially neglect higher order and work at tree level. Okay, and this window is bigger, the bigger alpha, but is smaller, the smaller n. Of course, if you are a UV person, you know the UV theory, you know that you can think of an abstract Platonic limit where alpha goes to 0. You factor out the leading order in the coupling. This goes to 0, alpha goes to 0, and then you have what you call tree level, which corresponds to the situation where essentially where your distribution is exactly this. Okay. However, in reality, you always have a finite alpha, and you can do a little exercise, and you will discover that the window where you can really say something only exists as long as n is less than 1 over alpha, which is the usual thing you're familiar with in perturbation theory, say in electrodynamics. You cannot go to arbitrarily high order. So this infinite set of sharp constraints exists only up to order 1 over alpha in the number of things. Now, so this is the case for a weakly coupled theory. In a strongly coupled theory, like you would have QCD, the pion Lagrangian, the corresponding coupling here is 4 pi. So it's such that all these loop factors are 1. Okay. So the window where you can neglect loop effects against tree level does not exist. Okay. So in a sense, in this situation, if you have an ordinary bread and butter strongly coupled theory, you cannot essentially extract any information other than the leading term, the one that is dominating the UV, the one from the first arc. Okay. And this is because you see in an ordinary strongly coupled theory, the distribution is something like this. Is totally there's no step like you have in a weakly coupled theory. So there's basically no transition between the UV and the IR. Okay, there's no clean separation between UV and IR contribution. In fact, what happens in a normal strongly coupled theory is that the Wilson coefficients are dominated in the far IR by the Lth loop contribution to them from the lowest coupling, the C2 coupling, okay? And essentially they go like the suitable power of the cutoff times the log to the L, where L is the order of your Wilson coefficient. In other words, in a strongly coupled theory and in the leading 1 over log approximation, the lowest Wilson coefficient drives all the couplings. This is the phenomenon that model builders know as strongification. Okay, it's also known that if you make the assumption that all the 3 couplings of the standard model, alpha 1, alpha 2, alpha 3, are strong at the same scale, then you can predict the couplings at low energy precisely with 1 over log accuracy, even if the theory at the high scale is strongly coupled. And in this situation, all constraints are automatically satisfied. The question, you see, is that these 2 hypotheses, weak and bread and butter strong, are UV perspectives on what can happen, okay? But the question is, I mean, we would like to have a purely EFT bottom-up perspective. That would make sense, right? I mean, without imposing any UV perspective. It's just working from the point of view of the low energy physics, like an experimentalist does. Okay, so in that sense, the question you can ask is: given S, given a certain energy at which the effective field theory makes sense, what can I say on the Wilson coefficients at that scale? Okay, so for instance, okay, what can I say in general without making any of these two assumptions? Okay, so for instance, at the tree level, in theories where you can set a meaningful tree level limit, you have this constraint that tells you that the contribution of the Wilson coefficients of higher order in any regime of validity of the effective theory have to be in decreasing size. Okay, if you go to the next order, you always have to get something smaller. By the way, this is true also in the bread and butter strongly coupled theories. Okay, as soon as you get one e-folding into the effective theory, you're already in the regime where this applies. Okay, so then the question is this true in general? Okay,
Riccardo, you have 5 minutes left, including questions.
Thank you very much. So the question is, one fair question is whether this property is true in general. By the way, one can write effective field theory and construct them based on some weird symmetry principles, which forces you not to have this. Okay? We call them super soft theories. They are theories that generalize the symmetry of the Galileo. Okay, so in principle, by arguing purely in symmetry on symmetry ground, you can imagine theories where this is not true. The question is whether this respects the prime principles that we're using here. Okay. So what I'm going to show here is a little study of this question. Okay, very limited. Okay, it's presented in our paper. It's based, again, we studied both the forward and non-forward case, but the non-forward case, at that time, I mean, now there are new remarks that I think can do it better. So I will only discuss in particular, this is the result obtained, the results obtained by Leonardo Rastelli, Simon Caron-Roux, Dalimil Mazak, and David Simons-Duffin. Okay, so staying in the forward region, okay, in this particular model, the amplitude takes this form. Okay, roughly here you have the running Wilson coefficients. These are running. The IS, it's just because SU crossing. Okay, forget that. Okay, details. Okay, these are just the running Wilson coefficient. This is a contribution that's coming from the Galilean coupling. I keep it here just to illustrate something below, but it will not play a role in this discussion because I will assume in my bounds that this is zero. Okay, it's consistent to assume it's zero. Okay, just for simplicity. And so these are the running. So these are just the running Wilson coefficients. Okay, where the betas are clearly like we are a derivatively coupled EFT. So the betas are just powers of the couplings of lower dimension because the coupling are all dimensionful. Okay, so C4 runs through the square of C2. Okay, and C6 runs through the cube of C2 and the product of C2 and C4. Very good. Okay, so this is just now in this theory you can compute the arcs and relate them to the quantities, to the Wilson coefficients. Okay, so what you have, as I write it here, you have this result where I show here for each arc of growing order there is essentially captures in a sense a corresponding Wilson coefficient of growing order. However, when you consider the contribution of IR loops, you get additional effects. And these effects can either be coming with positive powers of S, and I put them in the upper triangle of this equation, but they can also come with negative power of S and therefore grow in the infrared. These effects that grow with the power of S when S goes to zero, as I already told you before by that simple argument of power counting, start appearing with the second arc, with third arc, A2. Now, strictly speaking, there is already an effect with the first arc. It's logarithmic, okay, but it's already put inside the running Wilson coefficient. Strictly speaking, here there is a log, okay. Very good, okay. So now we have to, with this equation, we have to try to see what our constraints imply on the Wilson coefficients, okay. So in order to do that, we have to make some hypotheses. We're working, we always need hypotheses, okay. So a necessary hypothesis here is that all the Wilson coefficients are weakly coupled. In other words, the theory is weakly coupled. I mean, each Wilson coefficient is a coupling, okay? In the EFT, it's an energy-dependent coupling, and within the domain of validity, where we're asking our question, this should be weak. Otherwise, we don't know what we're doing. And now, this is unavoidable. Then there is another assumption that you can declinate in various ways, and it amounts to the fact that you cannot, in other words, you need to truncate above a certain order. Otherwise, you cannot do a study, because in this equation here, everything enters, okay? It's true that all the couplings are weak, but it could be that some couplings of lower dimensionality are weaker than some couplings of higher dimensionalities, and then those can be more important. So what I'm assuming here, what we need to assume is that above a certain order, things start becoming smaller and smaller, so you can truncate, okay? And of course, I don't have the time to explain the details of this. There are various ways in which you can do this hypothesis, at which order this happens, okay? In fact, the simplest of such, of this assumption you can make is what we call the simplest EFT, basically amounts to the fact that you assume that, and this is basically enforced by the hypothesis of weak coupling, but not completely, okay? We basically assume that you are in a regime where all the terms with positive power of S that come from loops are negligible, okay? While we certainly cannot assume that the terms that come with negative power of S are negligible, because if you go at sufficiently low energy, this will become large, okay? And then we run our program, okay? Our program working only for a limited number of arcs, which in this case is just the first three, okay? If you apply now the modify Hausdorff theorem, if you want, the positivity just amounts to this constraints, okay? This individual constraints. In this particular case, those matrices reduce to just a 1-by-1 matrix, and here you have the positivity of this matrix. And here what you get, okay? So of course you get the usual C2 bigger than 0. This is the old result, which was obtained many times, okay? And then you get the second one, okay, which is the positivity of the running second order Wilson coefficient C4, okay? And now this coefficient, as I said, runs logarithmically, okay? So in the far IR will always be positive because of the unitarity of the EFT. The running is due to the cuts in the EFT, and the cuts are unitary, so this thing grows positive. However, okay, as it grows positive in the IR, it may cross negative at some point in the UV. Okay. Now, all that our bound is saying is that if at a certain point this crosses negative, then there's no way you can believe your theory. And notice that this may happen in a regime where the theory is still weakly coupled. In the ordinary bread and butter strongly coupled theory like QCD or any other theories that, well, for instance, in some supersymmetric cases where we could have a handle on strongly coupled effects, this bread and butter works, okay? So anyway, in case where the bread and butter works, the point where this cross is negative is also the point where the coupling becomes strong, okay? While on the other hand, there is the possibility, I mean, this constraint allow you the possibility of having a theory where you cross the cutoff because of the breakdown of the consistency in the regime where it's still weakly coupled.
Ricardo, you're negative 3 minutes now.
Okay, I already went below. And
So
all I want to say
up?
is that let me just conclude that this super soft these constraints on the fact that this thing decreases is still true. In other words, that higher orders are always subdominant. This keeps being true. And there's another interesting situation where if you go to the last bound, let me just close here, right? This combination of Wilson coefficient, which at 3 level should always be positive, actually in the far IR becomes negative, and this is just a general result. But what can happen is that the constraint is such that it could happen that you cross the cutoff of the theory in a regime where this is negative. Okay, so in other words, you can have similarly consistent effective theory where the Wilson coefficient never and nowhere satisfy the 3 level bounds. And this is my outlook, and maybe I can answer the outlook if anyone asks a question. Even that I'm negative, I leave it here.
Thank you very much. It's a very nice talk. Yeah, I think we have time for a quick question or two, maybe from the audience or from the online crowd.
So maybe you could just clarify something that I didn't understand. The rigor of those bounds, were those bounds rigorous or? The rigor of the
they are rigorous. They are rigorous compatibly with the assumptions I've made. Now the bounds. By the way, the bounds on bread and butter are squiggly, but they're interesting. The bounds on weak coupling, they are rigorous and platonic.
Okay, thanks.
Yeah.
All right. I don't see any questions online. So I think in view of time, we should probably move on, but let's thank Riccardo for a very nice talk.
Thank you.
So the next speaker